So, in this couple of, I think there will be about 5 or 6 uh, practical lessons. I will show you and introduce the OpenGL in its WebGL implementation. The goal of this part of the course is both to practically um, implement what you see in the theoretical part, and with the final goal to teach you the basics about shaders writing. Um, as you probably should know at this point of the course, shaders are programs used to define a rendering pipeline in order to uh, rasterize, to visualize objects both in 2D, both in 3D, usually in 3D real-time graphics. So, in order for you to do this, we chosen to use this OpenGL, which is a software interface basically to your graphics hardware. It's not in itself a programming language like others. It's just a set of API that are implemented on a specific hardware of a graphic adapter. And this solution allows a good cross-platform performance for the product. So you can call the function provided by this API to define which are the models you want to draw. If you want to paint those models using textures or using colors, and performs basic operations like, for example, basic because they are not so complicated to do in OpenGL, but they are not basic at all. They involve matrix computation, so they are not that easy. But those are the functionalities that you can access by using OpenGL. The goal is usually to render in real time, 3D mainly, but also 2D images. Is not the only graphic interface currently on market. Of course, there are many others. The main competitor is probably the Microsoft DirectX, but it lacks the cross-platform capabilities OpenGL has. OpenGL is in fact available for a wider range of devices, ranging from tablets, computer, etc. OpenGL exists mainly in 2 different forms. There are the specifications and there is the hardware-specific implementation. Specifications are just the description of all the different functions, all the types, what we can expect, what it is expected that a function performs, while the other part, the library itself, is something that is implemented by the graphic adapter manufacturer, which by adhering to the standards of the API specification makes that particular graphics adapter compatible and supporting OpenGL. So AMD, NVIDIA, Intel, all of them basically support OpenGL. And this is why OpenGL can be so portable. So that's basically what you have. Specification, the drivers, and the implementation on a specific graphic card. In fact, many of the operations that are performed by the graphic adapter can be, and sometimes are, moved on your main computer CPU. Those are called usually software implementation of OpenGL. Usually the implementation of OpenGL is something that happens on the graphic adapter and then it is included in the graphic adapters, drivers. But sometimes you can move all the operation usually done and performed by a graphic adapter on your CPU, especially when you don't have such a powerful graphic adapter. And you have an example like Mesa 3D, which can be a software implementation of OpenGL. Software rendering, basically. The API standard, so all the specific about how the API of OpenGL should be and what we can expect from each of the function, is maintained by this Khronos group, non-profit industry consortium. It maintains a lot of open standards, for example, the Collada, which is quite widespread 3D model storing format. WebGL, OpenGL, OpenDR are all maintained by this Khronos group. Nowadays, they are improving the OpenGL standard, and probably in next year's course we will move from WebGL to Vulkan, which is an initiative from this consortium to improve some of the features actually provided by OpenGL. Even if Vulkan is a big improvement to the OpenGL architecture, but is not yet totally, since it's quite new, it was released the version 1.0 last year, so it's not been yet adopted by the industry. Also because many of the improvements are not yet required. Still, cross-platform moves a lot of the operation that still happens and are await on the CPU, on the graphic adapter, and there is the possibility to have, let's say, a faster interpretation of the shaders program than nowadays. But we will see what those terms mean in a couple of slides. OpenGL, just to give you a brief overview of the overall architecture of OpenGL, OpenGL is implemented as a client-server system. So we have a client-side part of the code, which is the application code, and it resides mainly on CPU memory. It's something that is charged over the CPU and the main processor, and a server side. Here we have all the operations concerning directly the rendering pipeline, and of course they are charged to the graphic card. Usually the client issues OpenGL commands which are executed in order to provide the final image. And sometimes this communication can happen through a network. And this is the situation where you have a thin client and you just receive from an external renderer just the final image. Basically, OpenGL is a state machine, so there is just one data structures that holds all the variables which are independent one from another. And one of the differences introduced with Vulkan is that we don't have any longer just one state machine, just one global state for all the running program of an OpenGL implementation, but since it is more object-oriented, there can be many buffers holding just the data structures. So that can be an improvement, even if more difficult to maintain as a coder. Having a state machine allows us to avoid the sending of too many arguments on each function's call. We will see this when we are going to program something in OpenGL, and also on both the client side and both on the server side. You will see why it can be useful to have expressed everything as a state machine. So when something is set, it remains set for all the lifetime of the application until you change that state. That's basically how does it works. And usually we have, for example, the command that enables something are just gl enable with an enumerator that tells which capabilities are switched on, and of course off. In the example, for example, it is enabled the depth test, so basically the backface scanning or not for some of the surfaces inside a scene, which is good when you don't have any transparency on your texture, but is otherwise a huge performance boost if you don't have to render those faces that in the end you are not going to see because they are blocked by other objects in front of them. Brief history about OpenGL. It starts in 1992 in Silicon Graphics. It was conceived in order to support the visualization of 3D contents, basically for scientific visualization. Later on, it was improved basically up to 2004 just by adding more and more and more capabilities. But at that point, hardware feature become so more powerful that this kind of approach was no longer feasible. Up to now, the rendering pipeline, so all the steps to be taken from the handling of all the primitives, vertex, faces, triangles, up to the final 2D image rasterized, was fixed. The steps was already predetermined. Given the complexity of the new cars, that approach was no longer feasible, and with this approach, flexibility was missing. So, when version 2.0 of OpenGL was released, there was the introduction of the GLSL, OpenGL shading languages, a very C-like programming languages, which has the purpose of programming just the rendering pipeline, to program the graphic adapter. And with OpenGL shading languages, you write shaders. And will be the topic of future lesson, because it's a big topic. With the introduction of GLSL, new API derived from the main and standard OpenGL specification. OpenGL ES, for example, was the first one in 2007. It was for the embedded subsystem. And in this way, the total API had to be stripped down in order to deal with the with systems that has a very limited range of resources. So because of this, many functions are useless on those systems, so they were stripped out. And in 2011, WebGL was added. It was based on the OpenGL ES, and its purpose was to bring inside browsers, inside any web browser, the capabilities of 3D real-time visualization. WebGL is the focus of this part of the course. OpenGL ES is just basically a subset of function and features of the standard OpenGL. For example, some complex operation concerning quads or other very complex polygonal objects are removed because they are not commonly founded on mobiles. And more importantly, OpenGL was able to provide an interface to the windowing manager and then and therefore on the graphic hardware of the mobile platform, which the standard OpenGL implementation does not. So you can program any graphic adapter, but in order to visualize the frame buffer that you fill with the colors of your image, you have to resort on the operating system, the specific operating system of that machine, in order to access and visualize what you created. Some example you don't have to know, but it's very different. It depends a lot on the operating system, so there can be a lot of different cases. That's one of the reasons we switched. In the first year of this course, we used the OpenGL straight, but there were a lot of issues in doing that. First of all, the specific implementation of OpenGL depends on the driver each of you had installed on his or her machine. It depends on the operating system. Many use the Linux, some Linux sub sort of operating system. Many have iOS, many Windows. So it was very difficult. We spent a lot of time dealing basically software assistance for having just the most basic setup work for each of you. So the problem was how OpenGL interacted with the windowing manager of your machine. WebGL instead utilized just the subset we described in terms of specification, works natively in all modern web browsers, including Edge. Up to recently, only the latest version of Explorer were able to access fully WebGL, and utilizes HTML5 canvas element for drawing, thus solving all the issues related to how to visualize the content of your frame buffer. You don't have any longer to install drivers that allow you to communicate with your operating system, asking him to reserve a portion of the screen for visualize your result. You just use the canvas element inside any browser window and you are able to visualize what you are creating. OpenGL, WebGL and OpenGL 2.0, ES 2.0 are the server part. The client part is programmed mainly using JavaScript, which is again another standard. While using OpenGL, you have to decide which is your client language. You can use C, and you have libraries for accessing OpenGL using C, C#. Basically, all programming languages have some sort of wrapper around the OpenGL drivers. But again, you enter in a wide variety of possibilities. So in this course, to test the concept of the theoretical part, we are going to use WebGL using Google Chrome. Just a decision to have a standard. But if you want to use any other combination, you have to use JavaScript. But if you want to use another browser, you are welcome to do that. Okay, so about the windowing. The OpenGL specification defines an hardware-independent interface, and that's a point. Otherwise, OpenGL cannot be cross-platform. It has to operate independently from the interface. So this comes with some limitation. First of all, you don't have any command directly in OpenGL or WebGL for handling the user input. As I said, no commands for performing any windowing tasks. You cannot open window, close window, or reserve any portion of the screen to draw on, etc. So, since you have to rely on the OS, too many possibilities, because there are so many different API being exposed by a given operating system. And this, as I told you, requires a lot of libraries, extra library, to maintain the communication between the two. Since we are taking advantage of the canvas element, we can, in this canvas element, script the rendering of any graphic we want to script. It allows us to have a frame buffer, which is a portion of memory over the GPU used to store temporarily the image that is going to be drawn. In the frame buffer there are more information than just the colors of the pixels, but we will see this later on. From the frame buffer you derive the final image that is shown on the screen. Supports this canvas element a lot of API, including those of WebGL. Has a width and an ID attribute, which seems for now not a big deal, but you will see they are quite important in order not to have any stretches or unwanted modification of your image due to the pixel size. And the area inside the canvas can be manipulated by using JavaScript. That the snippet of code shows you the tags inside any HTML5 documents required for just creating the canvas. After obtaining the canvas, then we have to create a context. The context is the data structures that keep tracks of all the state settings and the operations that we are going to perform. So we have a canvas. Attached to the canvas, we have a context. Those are the state values that can be set in a context. So, for example, if we are drawing a path, we memorize the context memorize, which is the current path that is being manipulated. How much this line that we are drawing is wide, which are the colors, if there is any alpha, anti-aliasing, blend mode, etc. All those information that you require while drawing in an area are stored inside the context. It can be requested using the JavaScript function on the canvas element. Once we created the canvas element, if everything is correct and we have a return value for this element, we can get the context from that pointer. Context ID, which is the name, if we want a 2D context or we want a WebGL context. Arguments are optional, not all the context require that you put any arguments in that. At this point we have the object as a return value from this get context function. We have the object that exposes all the API that we want to use for drawing. So here you have the example in any script. If you are scripting directly inside an HTML file, you declare a canvas variable and you get the element myCanvas, which is defined with the previous script, and once you have this canvas you can get a context from it. The name experimental WebGL has been kept for backward compatibility. Now the API is fully complete, so it's no longer experimental at all, but some browsers prefer that you ask for experimental WebGL and not directly WebGL as a context type. Now we have a frame buffer, we have a context, and we can begin to draw. How to draw? We have to specify the data that we want to visualize. The data that allows us to define the shapes that we want to draw. Remind that in this case it is a procedural drawing, so you have to specify the steps that brings you to the final image. Usually, this is done by the way of geometric primitives. In the HTML5 2D context, we just have rectangles and paths, both lines or circles, and that's it. And we can compose a figure by a combination of those two. Rectangles, just to give you a brief overview, you see we have the context. Dot means that we are accessing the context, and we require from the 2D context the function rect. Then we specify the parameters for this function, and in the end we hope to see something drawn. Fill is the same thing, but there is a color filling the rectangles, and just a borderline empty. The difference is the first one can be later on filled or stroked differently on the border. The other one is just the stroke. But, on the other hand, are just something quite similar. You begin a path, it's quite important because it resets. If you want to draw a path, then do something else, then start again to drawing a path, you need to use this function. Moving to, just move the pen to another point, the virtual pen, on another point on the screen. From that point, a line to draw a line to another point. Close path, since a path begins somewhere, if you close path from the last point to the first one of that path, can be closed. Arc instead can be used to create circles. Arc2 uses tangent, but just to give you an overview of the different commands. It's not important that you know, but just to introduce the topic. What it is important to know is the coordinate system, since each different context has its own coordinate system. The coordinates of the drawing space not always are coherent with that of the monitor, for example. But you know that monitor screen have in the topmost left corner the origin, and then the X goes from left to right, and the Y from top to bottom up to the screen width or the screen height. This is a canvas, and the coordinate system inside the canvas is coherent to that of the screen. Similar orientation, exactly that. It is expressed in pixels, as you can imagine, and it is the browser that converts everything you draw, the coordinates used for drawing inside the canvas, to screen coordinate. Something that is quite useful and is quite common. It's really difficult that you have to convert local coordinate inside your canvas, be it 2D or 3D, with a screen coordinate. So, for example, a point at the center of a canvas, like the point that you see, the blue point, has different coordinates considering the two different drawing spaces. Okay. Why it is? Because it is important, because in a way it helps you to avoid issues with different screen sizes. You just draw inside a canvas, and it's up to the browser, it's up to the operating system to convert what you see in the specific on the specific monitor that you are using. So let's stop for now for a while the theoretical part, and let's see how this works in practice. So code, let's create a new file. Let's create a standard HTML file. Okay. So, if you want to try to do this with me, you're more than welcome. This first part will concern just the 2D, and then we will see the 3D part. At least we introduce it today. That tag is just to say that we are using HTML5 without any. If you don't put it, your browser will try to best guess which is the version that you want to use. In this case, we avoid that problem. HTML. Okay. As you probably know, there are many parts in an HTML document. There's the head and a body and a footer. At least we don't need the footer, but the head and the body are required. Okay. In the head, we can probably just put a title for now. Okay, for now that's all in our head. And then we create the canvas object. Probably we can add before some style. Just to see the difference between the whole body and the canvas. So we don't want to have any CSS file, external CSS file, so we put some style in line. Okay, we put the background in gray. And then for the canvas instead, we gave it an ID because we need to retrieve this element from the JavaScript code. So we have to provide an ID. My canvas will do the work. My canvas. We need to provide a width. For example, 800. Okay, and height. And then we copy the style, but we put white. We can also insert here some text. Of course, the text is going to be shown only if the canvas object cannot be created. And then if you open it, you will see that there is a part which is gray, the background of the web page, and the canvas, which is the portion in which we are going to write. Ctrl Shift and J opens some useful tools. While programming in this way, it can be useful to have it in order to intercept some errors if you're lucky, because usually JavaScript errors may go silent or refer to something that is not wrong at all, but just happens to be on way of the compiler. So it's not that easy to intercept them. We need to add now the reference of a script to a script. Since we don't want to JavaScript inline and we want to keep everything in JavaScript on a separate file, we just, I don't know if you see, if you want, okay, it's better. Okay. Just the name. Okay, so now we need to add this JavaScript JS file. And when the body is loaded, so we use the onload method, the main function that we are to define into the drawing JS is called. So what we added now in this index HTML, okay. Okay. In the same folder, you just create a new file. And we have. So, in this drawing JS, we create a function. We are writing in JavaScript here, main, with a couple of functions inside. The first one is bar canvas. Document is a keyword that simply refers to the main document calling the JavaScript code. We get an element by ID, and the element is my canvas. So in canvas we are going to have the pointer that refers to this element here, got by ID. Okay. Then we create the context, and this canvas get context. For now we start with the 2D. By executing the code, it seems that everything is there, and let me check. Both the elements are correctly seen, so for now it seems no error. Okay, so we can start drawing. Let's do something. So let's say that I want to use something that is a little bit more complex than just playing around with the cursor, stroking lines. Let's see to make something a bit more complex. So x equal to 0. If x less than 800. Okay, this is just a for cycle. I think that all of you know what's that about. And that's how the thing works. We call context. We start by moving to x.0, the pointer. Context is right, move to is right. Okay. And then context dot line to x. Okay. If I execute the code now and there are no errors, I don't see anything. Simply because it is a state machine and we never issue the command of really draw it. We just moved around a cursor asking him for doing things, but never to paint really what we are doing. So for doing that, we again call context. And with the stroke, not line, sorry, but style, we define a color, which is gray, and then we ask for the painting itself. Now you should see, probably you need to, you see that we drawn some lines over the canvas. One thing that you should note is that the lines are not that perfectly drawn, even if they should be 1 pixel wide. They are probably 2 pixels wide. And with a trick, we can correct this issue. Now they are 1 pixel wide. Why this? Okay, this is because the pixels on your monitor usually they are squared, and the whole number coordinates define the edges of those squares. So if you want to draw something just 1 pixel wide between whole number coordinates, it will overlap the total of 2. You see the red line, it is overlapping, it's an edge for 2 columns of pixels. So this is your intended line. Instead, this is what you get, because the monitor cannot lift just half of a pixel. A pixel is lit or not. So it has to switch on 2 pixels. Instead, if you use a half number 0.5 that you have seen, the line that you intend to draw falls exactly in the middle of the pixels. And in this case, there are no mistakes on which is the pixel that you want to switch on. That's just something to show you how all this stuff works. Okay, we can do basically the same also for the y coordinate. So y but we have of course to change coordinates, and so this is going to be 0 and this is going to be 800 y. Okay, we created something like this. I think we can take a 5-minute break and then we see something more complex, and then we switch to the 3D part, which is much more interesting.